Statistics for Business and Economics. Chapter 8, Interval Estimation. In this chapter, we will cover the following topics: interval estimation for the population mean in the case where sigma is known, interval estimation for the population mean in the case when sigma is unknown, determining the sample size, and interval estimation for population proportions. In the previous chapter, we learned how to do point estimation. In this chapter, we are going to extend that concept to do interval estimation. So the first concept we need to do is the concept of margin of error. Margin of error and the interval estimate. A point estimator cannot be expected to provide the exact value of the population parameter. An interval estimate can be computed by adding and subtracting a margin of error to the point estimate using this formula: point estimate plus minus the margin of error. And later on, we're going to learn how to calculate this number, margin of error. The purpose of an interval estimate is to provide information about how close the point estimate is to the value of the parameter. Margin of error and the interval estimate. The general form of an interval estimate of a population mean is given by the formula that we said before: the point estimate plus minus the margin of error. In this case, the point estimate is the sample mean, and the margin of error, we are going to learn how to calculate this number in the next few slides. Interval estimate of a population mean, sigma known. In order to develop an interval estimate of a population mean, the margin of error must be computed using either the population standard deviation sigma or the sample standard deviation S. Sigma is rarely known exactly, but often a good estimate can be obtained based on historical data or other information. We refer to such cases as the sigma known case. And this is the case we're going to be focusing in the next few slides. The case when we know sigma. And maybe we don't know sigma exactly, but we have a good estimate that can be obtained based on historical data or other information. This figure here is at the heart of the way we're going to build the margin of error. This curve represents the distribution of the sample means. And remember from the previous chapter that we know the conditions under which this distribution is going to be approximately normal. And also remember that under those conditions, the standard deviation of this distribution is given by this number, sigma x bar. And the expected value or mean of this distribution is equal to the population mean. Remember that we may or may not know this value, the population mean, and in most cases we want to estimate it. We also know that the area under the graph of the distribution is equal 1. Think about the following. If the area in between these two values is 1 minus alpha, then we will have an area equal to alpha outside the interval. Due to the symmetricity of the distribution, then I will have half of that area on the lower tail and another half on the upper tail. As an example, you can think about picking this value alpha equal to 10%. Then 1 minus alpha will be 90%. And then we are asking ourselves, what are the values here on the x-axis such that the area in between these two values is 90%. If the area in between these two values is 90%, then the area outside this interval is going to be 10%. And half of that area, 5%, is going to be on the lower tail, and another half is going to be on the upper tail. And the question is, how do we compute these values? These values are going to be calculated using this formula. This formula is a product of a z-score that has the property that on the standard normal distribution we have an area of alpha over 2 on the upper tail. We already know how to calculate this z-score because we know how to use the standard normal table. But later on, in a few slides, we're going to see a more detailed table where we give a better description of how to calculate these values. From the previous slide, we know that there is a 1 minus alpha probability that the point estimate is going to be in between these two values. And then, if we select a point estimate and is in between those two values, and then around this point estimate we build an interval with this length to the right and this length to the left, then we know that as soon as the point estimate is inside this interval, the interval that will be around that estimate is going to contain the population mean. And if that point estimate is outside the interval, then it's not going to contain the population mean. And the probability that this point estimate is outside this interval is alpha, with half of that probability that the point estimate is going to be on the lower tail, and another alpha over 2 probability that the point estimate is going to be outside the interval. In this slide, we give a detailed description of how to calculate the interval estimate for mu and how to calculate the margin of error. So remember that the interval estimate is built by taking the point estimate and then adding and subtracting the margin of error, and this is the formula we're going to use to calculate the margin of error. In this formula we have the critical values, C alpha over 2, that we described in the previous slide, and then the standard error of the mean. Remember that the standard error of the mean is the population standard deviation divided by the square root of the sample size. Also remember that we are in the case sigma known, so we know this value here. Now, the description of this formula is x bar is the sample mean that we know already. 1 minus alpha is what we call the confidence coefficient. C alpha over 2 is the C value or the C score, providing an area of alpha over 2 on the upper tail of the standard normal distribution. Sigma is the population standard deviation, and n is the sample size. And the margin of error is calculated using this formula. Now, the only thing is left to do in order to know how to calculate precisely the margin of error is to remind you how to calculate these critical values. The most commonly used confidence levels are 90%, 95%, and 99%. The confidence level is 1 minus alpha, remember. If 1 minus alpha is 90%, then alpha is 10%, and then the area left on each tail is 5%. Then, in order to calculate this value C alpha over 2, you need to go to the standard normal table and find the value so that the area to the left is 0.95 or 95%, and that value is 1.645. If the confidence level is 95% or 1 minus alpha, then alpha is 5%, the area left on the tails is 2.5% each tail, and then the value that you need to look up in order to calculate the C-score is 0.975 or 97.5%, and this is the value. Finally, for the confidence level 99%. 1 minus alpha is 99%, so alpha is 1%. The area left on each tail is 0.5%, and the lookup area that you need to find the z-score is 0.995 or 99.5%, and the z-score that you will find is 2.576. I will encourage you to memorize these values together with the confidence level. So for the confidence level 90%, C alpha over 2 is 1.645. For the confidence level 95%, C alpha over 2 is 1.96. And for the confidence level 99%, C alpha over 2 is 2.576. Now these values C alpha over 2 are in some texts referred as critical values. Meaning of confidence. Because 90% of all the interval constructed using this margin of error will contain the population mean, then we say that we are 90% confident that the interval that we build, again using this, includes the population mean mu. We say that this interval has been established at the 90% confidence level. The value 0.9 or 90% is referred to as the confidence coefficient. Adequate sample size. Now this and the next slide are just to remind you what are the conditions under which all this is true. So remember, in most applications, a sample size n greater than or equal 30 is adequate. And this is for the case when the original population is not normally distributed. Okay? If the population distribution is highly skewed or contains outliers, then a sample size of 50 or more is recommended. Then, if the population is not normally distributed but is roughly symmetric, a sample size as small as 15 will suffice. If the population is believed to be at least approximately normal, then a sample size of less than 15 can be used.